All right, guys, thanks for tuning in. Part 2 of Electric Fields 5.1. We're going to cover electric current in this video and the potential difference. All right, these are the equations from the data booklet we're going to hit. This is current. This is the equation for current. Current is the symbol I. It has units amperes, capital A for the ampere. This is a change in the number of charges, the change in the charge over the change in time. It's the flow of charges. We have the potential. Potential is a scalar. The potential, electric potential, is also known as the voltage. Electric potential or electric potential difference, this is known as voltage. Has units of the volt or the joule per coulomb. Joule per coulomb. And then we have our drift velocity equation. This is still current. N is the density of charges. A is the cross-sectional area of your wire or whatever the charges are flowing through, cross-sectional area. V is something called the drift velocity. And Q is the magnitude of the charge, the charge magnitude. All right, we'll cover these equations in greater detail on the upcoming slides. All right, potential difference. Electric charge is experienced in electric force, the Coulomb force. And so when a charge is moved close to another, work is done on that smaller charge. Look, I have this big charge Q right here, and we have little q. So work is done in moving little q around big Q, because big Q creates this electric field. So the potential difference V between 2 points, let's say between A and B, is defined as the amount of work done per unit charge in moving this little charge from A to B. This is the equation for potential difference. The potential difference, V, aka the electric potential, the voltage, equals work divided by Q. The units for the volts for electric potential are joules per coulomb, which are equivalent to volts. So this is voltage, not in the circuitry sense, but you have a potential difference between A and B. And note that this is a potential, electric potential is a scalar quantity. All right, practice problem 1. This looks familiar. The uniform electric field strength inside two parallel plates is 275 newtons per coulomb. The plates are separated by a distance of 2.5 centimeters. A plus 12 microcoulomb charge having a mass of 0.25 grams is placed in the field at A and released. A, calculate the speed of the mass once it reaches the negative plate. So we are going to first, we need to get, well, actually we have the acceleration. We have the acceleration of this mass from before. We could quickly get it again if we do E equals F over Q, solve for F, get this is the electrostatic force, the difference between the weight, the difference between the electrostatic force and the weight of the object, F sub g, gives me the net force. Then I can divide away the mass to get the acceleration. And then this becomes a kinematics problem because I know that the distance is 2.5 centimeters. I will need to convert that to meters, which has already been done for you here. So my displacement is 0.025 meters. I have the acceleration. I know that the initial velocity, the u, is 0 because I'm assuming it starts from rest. So I can calculate the final velocity. Part B, determine the potential difference between the plates. Okay, so we're looking for the voltage. Voltage equals work done divided by the charge. So how do we get the work done? Do you remember this? Work equals the change in kinetic energy. So to get the work, I'm going to have to get the particles, or I'm sorry, the masses change in kinetic energy. At the start is A, and initially it has E sub k, delta E sub k equals E sub k final minus E sub k initial. Well, the initial is 0 because the speed is 0. So calculate the final kinetic energy. That will tell you the work. Divide by the charge, and you have the voltage. But don't forget, do your conversions. Please, I stress this. Make sure you convert. Question number 2. An electron is accelerated through a potential difference of 2.5 MV, megavolts. You better check the data booklet if you don't know what mega is. What is the change in kinetic energy of the electron? The change in kinetic energy. This is the work. So V equals W over Q. Ooh, can you see that? Yes, you probably can. So V equals the work done over Q, and work equals delta E sub K. Okay, so we're looking for work. In this equation, the work of the field caused the change in the kinetic energy. That's what work does. It causes a change in kinetic or potential energy. So then it just becomes an issue of relating all of these prefixes. Solving and getting the correct prefix, use the front of your data booklet. Okay, let me introduce you to the electron volts. So in speaking of terms of energies of individual particles like electrons and atoms, rather than just like large groups of charges such as current going through wires, joules are too large. A joule is actually a pretty large unit of energy. So rather than discuss individual particles in terms of their joule energy, they are discussed, the energy associated with these particles is the electron volt. It just makes more sense. So the electron volt is the work done when moving an elementary charge E, it has the magnitude 1.6, E negative 19, through a potential difference. So work is Q times V, and I can see that the 1 electron volt, which is a unit of energy, I've told you, the unit of energy is equal to the charge of the electron, that's the Q, times 1 volt. So 1 electron volt is just 1.6 E negative 19 joules. It's the same as the charge. That value, obviously, because 1 times the charge is 1.6 E negative 19. So it's really easy to convert from an electron volt to a joule. You just multiply by the charge. Okay, so put this in your data booklet somewhere. And note that we will be using electron volts a lot in topic 7 when we get to nuclear physics or atomic physics. Question number 3. An electron is moved from point A, having a voltage, a potential of 25 volts, to point B, which has a potential of 18 volts. What is the work done in electron volts and in joules on the electron by the external force during the displacement? So the work done is V times Q, or Q times V, where V is the potential. In this case, we will use the potential difference. Sometimes I'm going to stress it as delta V, so just get the change from B to A. So you'll do the voltage at B minus the voltage at A. That gives you your potential difference multiplied by the charge of an electron, and that'll tell you how much work this external force had to do. Okay, then for part B, we're going the opposite way. In part B, we release the electron, and the electron goes from its position B back to A. We release it, there's no more external force. Instead, it's just the field that's causing the electron to go return to position A. And so I want you to outline the changes to the electron's electric potential energy and the kinetic energy due to the work of the field. So originally, the the particle is at rest at position B. It moves from rest and it strikes point A at some speed. So tell me how the kinetic energy changed. Did it go up or did it go down? What about electric potential energy? Well, even though we don't really discuss electric potential energy in SL physics, it's just really HL physics, I'll tell you this. When a particle is, when you have a negative charge like this electron, it wants to be towards a higher voltage. That's a more positive voltage. So electrons or any negative charges are attracted to high voltage or more positive voltage. When the electron is at a low voltage or a negative voltage, that has a lot of potential energy. Have higher potential energy, because what happens is you let that go and it will move away. It's kind of like squishing a spring, if you will. If you push the spring in, when you let go of the spring, it's going to immediately drive back out. So for the electron in this case, think about the electron is at a low potential at B. It's a more negative potential. And then it moves to a more positive potential. What did that do to the electric potential energy of the electron? Did it increase it or decrease it based on my descriptions? And if that wasn't enough of a hint for you, I have one more, a very important topic that you really should write down, especially if you are going into physics in college. The work of fields, the work that fields do to objects typically decreases an object's potential energy and increases its kinetic energy. That's how fields work. All right, let's just talk about the nature of charge flow really quick. Materials can be divided into three categories. We have conductors, which easily transport electrons, non-conductors or insulators, which impede electron flow, and then semiconductors, which do both and give us really awesome computing power. In general, metals are conductors, non-metals are good insulators, and metalloids are good semiconductors. So, introduction to electric current. It is the time rate at which a certain number of charges are passing a certain point in a circuit. So this is the equation for electric current, change in charge or charge flow over time. So you can see this nice GIF here shows what I'm talking about. I could choose like an arbitrary line in this copper wire or this current carrying wire, and I would just choose a point or this line, and I could just count the number of charges that are passing by in a second. And I could take those number of charges and multiply by the charge, the number of particles multiplied by the charge and divide by time, and I would get the charge flow. From the formula, it should be clear that current is measured in coulomb per second, which is the ampere. Remember, the ampere is the fundamental unit. The coulomb is the derived unit. So an ampere times a second is a coulomb, and a second, of course, is also fundamental. So if the previous slide wasn't easy for you to understand, I have a second slide on current. So I want you to think of conductors maybe as pipes that hold electrons. Even though this isn't totally an accurate view, it can work. And we would have a chemical cell, like a battery or some type of driver that would push electrons out of a negative side, and these electrons naturally repel each other. So if you have a bunch of electrons getting pushed on at one end, they're going to push on every other electron. So this is how current works in the most simple sense. Just electrons pushing each other down a tube. The electromotive force is transferred simultaneously to every charge in the circuit. The electromotive force is not a real force. It used to be called EMF, the electromotive force, but really it's voltage, it's potential. It's like a push, if you will, but it's not force. We'll go into more detail on voltage in a circuit in topic 5.2. We take circuits and electricity for granted because it's so common in our society, but there was a time where not much was understood about current. It wasn't until 1916 that electrons were identified as the charge carriers in the metal. This was, of course, Tolman and Stewart. So assuming charge carriers in a conductor are free to move, if a conductor is suddenly accelerated, the electrons would pull, like they would all bunch up at the trailing end due to their inertia, and a potential difference could be measured by something called a voltmeter. A voltmeter measures voltage, would be set up between the ends. So we would have a voltage created just by, moving a piece of metal. So you could imagine, just like that, these electrons have inertia. They resist a change in motion, and so if I just suddenly accelerated a metal forward, these electrons should bunch up at the end. In a metal, free electrons move very rapidly. They collide constantly with atoms in the crystalline lattice structure of the metal. So we're talking at the molecular level. Imagine these little bumps are like various atoms, crystals, and the electrons kind of like move all throughout, like they flow, kind of like water, if you will, around these atomic structures. The current through any cross-section of the conductor, the net current is zero, because look, the charges are just moving in a chaotic manner. They're not moving in a particular direction. And so if you analyzed their overall, how many charges are moving in the same direction over time, it would be zero through this cross-sectional area, this rectangle that's moving laterally on the screen. So although electrons have a very, very high velocity, the net result at the macroscopic level is that there's no net electron migration through metallic conductors. So let's say we take that conductor, and rather than accelerate it, what if we apply a potential difference, a voltage at each end? So we could have, a high potential here, even though the electron would actually want to go towards that high potential. And we would have a low potential here. I'm just following the schematic. So the electrons of their own accord would just slowly kind of drift. Like, just imagine I just have like 2 alligator clips, I don't know, and I just give them a little push. They would slowly want to drift towards that lower potential. The net current in this case would not be zero. The electrons would still have a high velocity, but this time the net migration is in general towards the direction of this lower potential. When we talk about things like current, our signs are going to reverse. So inside of a circuit, because of Benjamin Franklin's original conventions, he thought that the positive charges are what move inside of a conductor. We still follow that convention, even though nowadays we know that it's the negative charges that moved. But again, we didn't realize that until 1916. Anyways, the speed of this net migration is known as the drift velocity. Drift velocity. So if we know the number in a free charges Q per unit volume, this is the number density. N is the number density. The number of charges per volume, and the cross-sectional area A of the conductor, and the drift velocity V of the charges. The current then is given by this equation. I equals N, that's the number density, times the cross-sectional area, times the drift velocity, times Q. Question number 4, an ohmic conductor. Don't yet know what that is, but we will get to this in 5.2. It's connected to an ideal ammeter. Don't yet know what that is, but we will get to that in 5.2. An ammeter is just something that measures current, and an ideal ammeter measures current without messing up the current in the circuit. So it offers no resistance. That way it just gets a good read. Of course, they don't really exist. And to a power supply of output voltage V. The following data are available for the conductor. We have the density of free electrons. This is the N. Note it's 8.5 times 10 to the 22nd inverse cubic centimeters. So that's number of electrons per volume. We have the dimensions of this conductor. The conductor is the boxy shape, that rectangle. The length is 10 centimeters. The height is 0.02 centimeters. The width is 0.02 centimeters. They give us a lot of dimensional information. They want us to calculate the drift speed V of the electrons in the conductor in centimeters per second. Well, that's good. That means I don't have to convert these units. State your answer to an appropriate number of significant figures. Okay, they're actually asking for sig figs. So we will use the equation I equals the number density times the cross-sectional area, so figure out which dimensions you're going to use to get the cross-sectional area, times the drift velocity, that's our target, times Q, which is the charge of an electron. Get that in front of your data booklet. I isn't given because this was a two-part problem, and in part A, you calculated the current. So I will just give you a value for current. The current in this case will be 5.0 milliamps. Milli, meaning 1,000th of an amp. Calculate V. All right, so once you're done with the 4 practice problems, put those into the red basket. They will be graded. Now, you will pick up the E-Field simulation packet from the blue basket, and you will complete the simulation. It's a PhET simulation. You'll find it on the homepage of the Hub. You'll submit that simulation to the basket on my desk, the red basket, by the end of the week. This is a screenshot of the charges and fields simulation. Here's the thing. I ask you in the simulation to do something with what are called equipotential lines. Equipotential lines are places in the field where the voltage or the electric potential is the same. So I'm going to have you play with this simulation even though equipotential lines are a topic for HL physics. You guys will learn it too. It's not bad. So this is an image of an electric field emanating from a positive charge. We're used to seeing these field lines. It's a radial field. These circles with the dashes, do you see them? These circular lines around here, these are equipotential lines. They are places in the electric field. If we walked around, the voltage would be the same. The voltage gets higher the closer you get along the field lines. And the voltage for the positive charge. And the voltage for the positive charge gets lower the further you go away. Now this is not a uniform field, and so the places where you have the same voltage anywhere around the charge is in a circle. For parallel plates, the beauty of parallel plates is that these equipotential lines would just be like that. It would be totally perpendicular straight lines, versus the equipotential lines for a radial field are circular. So these are places where the voltage is the same. And that's the only extra piece of information you need to complete the packet. I hope you found this video helpful. Thanks for watching. Study well.